Hello, my name is Marissa Gibides, and I'm a junior at West Virginia University. Today, I'm going to be presenting on my research I've been doing with Dr. Bobko entitled Development of Non-Invasive Oxygen Imaging Approach using Water-Dispersible Micro Lithium Naphthycyanine Probes. Blood flow affiliated with tumors is irregular due to the presence of widened vessels and large intercapillary distances, which you can see in this middle section of the photo. This results in hypoxic areas within the tumor. These areas are oxygen deficient and are known to have ruinous effects on curative treatment to control cancerous tumors. The use of oxygen mapping will allow for prediction to be made on the effectiveness of anti-cancer drugs before the start of a treatment, since it will reveal any hypoxic areas. It's also not possible to measure real PO2 in a removed tumor, which is ex vivo, since it's no longer in its true natural environment, which is inside of a living organism. There are multiple different methods for oxygenation monitoring, which include widespread bold MRI, positron emission tomography, which both measure perfusion, the rate at which oxygen is being delivered to the tissue. And then there's NMR spectroscopy using perfluorocarbon, and electron paramagnetic resonance, EPR. These two measure steady state consumption, which is a balanced value between oxygen delivery and consumption. EPR stands out from the rest of these methods because of its high sensitivity to PO2, direct measurement of oxygen, and high functional specificity. For EPR probes, they can either be solid or soluble. The advantage of solid probes over soluble ones are that they are stable for a longer period of time in the tissue, have low toxicity, a good signal intensity, and show high sensitivity to oxygen. The current problems with these methods are the unequal sizes of the oxygen-sensitive probes and their hydrophobic surface. For oxygen imaging experiments, it's extremely important to have a uniform particle size. A particle with a diameter twice as large will provide a signal intensity that is 8 times higher. This results in particles with larger diameters overshadowing signal from the smaller ones. Then, because of the hydrophobic surface, this results in the probes not being able to disperse in water homogeneously, have an equal distribution in tissue, and be biocompatible within the tissue. Here in picture A shows the chemical structure of our compound, our crystal compound used to create our probes. Picture B is a microscopic image of the particles prepared using sonication techniques dispersed in complete cell media culture. Here it is evident that the particles do not have a homogeneous distribution or size. To create homogeneous particle size, the approach of microfluidics was used. Microfluidics produces highly uniform microparticles with a very narrow size distribution, which you can see in this slowdown video right here. The particles are made by the water phase, which are these two, bisecting the oil phase, which is the horizontal one. The particles can be generated with a wide range of diameter sizes, depending on the chip and pumps used. Microfluidic techniques for the preparation of the particles allow for the creation of uniformly sized particles. These pictures show how the particles shrink after formed by microfluidics as the dichloromethane, which was mixed with the crystals to create the oil phase, evaporates. And when it's done evaporating, right here, you can see the particles have a homogeneous size. This slide shows data which proves the particle size is dependent on microfluidic parameters. This first graph displays the size dependence on the rate of the water phase. As the rate of the water phase increases, so does the particle diameter size. The middle graph displays size dependence on the rate of the oil phase. As the rate of the oil phase increases, the particle diameter size decreases. The last graph right here displays the size dependence on the crystal concentration. As the concentration of the crystals increase, so does the volume of the particles. These graphs also show how the diameter size of the particles depends on the rate of the oil phase. On the picture on the left, the nozzle size is 100 micrometers, which is the diameter of the tubes within the microfluidics chip. The graph on the right has a nozzle size of 30 micrometers. Even though the nozzle size is different, both graphs display the same trend. In conclusion, the best way to fix the first problem of non-homogeneous particle size is with the use of microfluidic techniques. This results in a narrow particle size distribution, which can be set to any size by changing the preparation conditions, and it allows for the preparation of highly concentrated dispersions. This is evident in the picture on the right, where the particles were made using microfluidic techniques. The particles on the left were made the older way of sonication, where sound waves are used to create the particles. Next, for the issues of bad dispersibility in water and unequal distribution in tissues caused by the hydrophobic surface of the crystals, the approach of tuning the surface properties of the particles was used. The surface properties influence biocompatibility and cell-particle interactions. With the use of polymers of different properties, the surface of the particles can be modified. Bare particles and two different polymer-coated particles, polydopamine hydrochloric acid, were used. Without any polymers, the bare surface is very hydrophobic. The polydopamine coating leads to strong interactions with the cell surface and better distribution during tumor growth. The hyaluronic acid coating binds to the PDA-coated particles due to its negative charge being attracted to the PDA's positive charge. This causes the particles to now be hydrophilic. Hyaluronic acid is also natural to the cell's environment, which improves the particles' biocompatibility. For the creation of the PDA coating, polydopamine was formed by dopamine autooxidization. The conditions were dopamine 10 millimole, piperidine 20 millimole, and methanol. Then the microparticles were incubated for 24 hours 3 times. The hyaluronic coating was created by the PDA-coated particles incubating in the presence of hyaluronic acid overnight. For tumor installation, a mixture of PYMT mammary tumor cells and microparticulate probes was injected into the mammary fat pad. The tumor size was then measured weekly. Our results show no difference in tumor growth rate for the tumors that were injected with coated particles compared to the tumors with no particles at all. This indicates good biocompatibility since the coated particles did not interfere with the tumor's growth. The uncoated particles, however, slowed down the tumor's growth, which indicates bad biocompatibility between the two. These pictures show the conditions of the EPR used on the tumors. The picture on the left shows the EPR spectrum of the particles, and the graph on the right shows the dependence of the EPR line width in partial oxygen pressure. On the left is a 3D view of an oxygen map of a tumor. The middle picture is a 2D cross-section of an oxygen map of a tumor. The black areas within the tumor are hypoxic, oxygen deficient, and the white areas on the outside are normoxic, meaning they have a normal oxygen concentration. The graph on the right shows the relationship of the number of pixels for different amounts of PO2. PO2 below 10 is hypoxic, and 20 and above is normoxic. This project is still ongoing currently. In the future, there will be EPR image reconstruction, functional map calculations, and evaluation of particle distribution within the tumors. In summary, the preparation of uniformly sized oxygen-sensitive microparticles was created and coated with polydopamine and hyaluronic acid. The PDA and HA coatings were found to be the most biocompatible with the tumor compared to the bare particles. And acknowledgements to Emily and Timothy for animal care and cell culture, Oksana and Mark for EPR imaging. Thank you for your time and listening to my presentation. Feel free to ask questions you may have in the comments down below.